Hello everyone, good morning, good afternoon, or good evening to all of you. Let's proceed with the Altair student webinar series, getting into Altair SimLab. My name is Rafael Silva and I'll be the panelist for this session. When we talk about SimLab, we're talking about an environment where you can go from the creation of your finite element models until analyzing the performance of really complex assemblies, such as this suspension system right here, where you can run multiple physics, including structural, thermal, electromagnetics, and fluid dynamics, which can be easily set up using highly automated modeling tasks. So just talking about these three examples right here, I have my suspension system, most of my parts included here, and I want to verify what is the response of the system to specific loads that is being applied. So I have here, let's say, my upright, my brake disc, and my brake caliper, my wishbones also. And I want to add some inputs such as the braking force or the cornering force or my bump force and verify the response to all this loading. What is the displacement of the system? What is the deformation and the stresses caused by those loads? In terms of physical problem, this can be understandable using mathematical models to define those physical problems that I want to understand. And to solve my mathematical equations or my mathematical model, finite element methods is one of the methods that you can use to really make it easy to calculate all those equations that is being taken into account on those assemblies or complex models that you're trying to simulate. In my top image right here, I'm trying to understand the temperature distribution whenever I add, I have my printed circuit board right here with all the components, and they have some heat dissipation and also heat generation loads, which I want to add to my assembly to verify what is the temperature distribution throughout all my components. All right, so talking about the finite element method, the first thing that comes into my mind is how to define precisely a finite element model. And for that, we begin with the system idealization, which is simply going from your physical problem as the suspension system that we had in previous slide. And with that physical problem, we want to build a mathematical model to represent the behavior of that physical problem. To build that mathematical model, we need to add some hypotheses to it, such as what is the geometry, what are the material laws, what are the loads, and the kinematics. After you've built your mathematical model, then you can solve it. And one of the ways to solve a mathematical equation or a mathematical model is using the finite element method, in which you will reduce the problem complexity from a continuous geometry to really discrete geometry such as tetrahedron or hexahedron elements, which are the names that we give to those really tiny pieces of discrete geometries that we find in the finite element approach. Then we have the mesh density specification, which is simply the mesh size. Then we can define our solution and the parameters involved in the simulation or calculation that we want to do. And for that, we can represent our loads and boundary conditions. Exemplifying here a structural analysis where we've talked about the suspension system. We have our physical problem, which is mainly my suspension system is I want to evaluate the response due to some inputs such as the cornering or the braking force, and this will be my physical problem. And for that, I can build a mathematical model. As an exemplification here, Newton's law, where it takes into account the acceleration, the velocity, and the displacement. This equals to a force that varies along the time. And first things that we want to do as a system idealization is ask a few questions, whether I want to solve this problem as a linear or non-linear, whether I want to solve it as static or dynamic, and also having consistent unit system throughout your whole workflow. So we have a geometry that is imported in millimeters, let's say. I need my material laws, I need my loads, I need my initial conditions all to be within this same unit system so that my result at the end will be consistent. All right, so we have this physical problem right here, a really complex one to solve, but in the finite element methods, as I mentioned, we want to reduce this complexity by representing all these parts, all these tiny parts, such as the beams right here, with specific elements, such as a 1D representation or shell elements or solid elements. And one thing that you need to ask yourself is, what type of elements should I use to represent it precisely, this problem? The first thing you need to understand is what are the outputs that you want to get out of this simulation. If it's simply a displacement, then 1D element representation will be just fine for you. Answering some of the questions that I've asked in the system idealization part, how to define my problem in terms of if it's linear or non-linear, if it's static or dynamics. Let's go into it right now, comparing both of them and understanding where and when should you use linear or non-linear, static or dynamic. So starting with the linear part, our fundamental condition is that the stiffness matrix remains constant along the analysis, and that means that we have proportionality between causes and effects. This stays as a constant value whenever I take, for example, my force divided by my displacement. This will remain constant throughout my whole analysis. On the other hand, my nonlinear, this is really a good example of a nonlinear problem. We have all these three nonlinearity sources displayed right here. So the nonlinear fundamental condition is that the stiffness matrix will vary along the analysis, comparing to not varying. And there are three sources of nonlinearity, which is material. Whenever your material is exiting the linear behavior and starting with the plastic behavior, it will cause nonlinearities and changes in the stiffness. Geometric nonlinearities, which is whenever you have large displacement, the stiffness will also change because you're changing the shape, let's say, of your body. Such as this example right here, the stiffness is getting higher and higher whenever I press this down. And also contact nonlinearities, which is you can deal with friction coefficient. You have this sliding contact that has some friction on it. This represents nonlinearities. And also whenever you're dealing with an open gap, what I mean about that is you have two components which they don't touch each other, nor virtually nor physically, and when you start pushing one to another, it will get into contact between each other, and this will increase the stiffness of your system, and this is also one of the causes of nonlinearities. The other question is if it's static or dynamic, and mainly whenever we're dealing with static, our first hypothesis is that the mass or the inertia effect does not take into account our simulation, so it's neglected. Also, our velocity times the coefficient, the damping coefficient. So basically, we have our force equals to our displacement times our stiffness. The dynamic event, in other hand, the inertia effects are really important. We have this weight distribution and weight transfer during the simulation process, and the time period also affects the results. So we have our full Newton laws equation right here. As we can see here in this example, this is something that needs to be dynamic because I have this weight distribution going from the back to the front after the impact, and I also have at certain time frames, time steps, specific values for stress and displacement and deformations, all that included. So we can see here at time 0 we have no deformation at all, but once it reaches 0.12, let's say, the final time right here, we have the maximum deformation. Now going through some engineering applications, I have one here to show you right before we do some demo using SimLab. We have this belt sander, which is mainly used to smooth the wood. And this is a really complex problem. We have a lot of parts involved in this. We have the interior of it, which is we have some electronics. We have an electric motor also. And in the outside, we have this cover made of plastic. So simulating that is really complex. And we have the result right here that I wanted to show, the complexity of the things that we can do in terms of simulation. So the outer case, which is made of plastic, we can simulate basically the injection molding of it, adding the fluid, and see how it is acting, the filling time, the cooling time, and the temperature distribution after a certain period of time. With that temperature distribution, we can add some constraints to evaluate the warpage. So deflections to your component just based on that temperature distribution that resulted from your injection molding simulation. We can do a nonlinear event such as this 3-point bending, evaluating the stresses and deformations due to a bending test. We can analyze also the fluid dynamics internally. So we have this electric motor with a certain rotation, and we can evaluate the temperature distribution due to that flow that is caused by that rotation internally. We can also evaluate the durability and resistance to drop tests, so to drop impacts. We're dropping this component from a certain height, and we want to evaluate the stresses and deformations in case we have plastic deformations, and also the package inside, how all the components is resistant to that specific load that we're applying right here. So all this can be used to design a single piece. In my case here, I'm designing just the exterior of it. I'm just simulating the outer casing, which is made of plastic. And as you can see here, the complexity involved in simulating these kinds of components, it's immense. And we can use the finite element methods to really reduce that complexity in terms of equation calculation. Going into SimLab, let's see how this workflow that we've talked about in terms of physics problem, mathematical model, and FEA workflow goes into this software right here. In our demonstration, I'm going to use this simple model. It's not even an assembly, but for the purpose, it will be enough. In my case here, I'm going to do a linear static event and also heat transfer. And then I'm going to overlay the temperature results from my heat transfer to my linear statics. Okay, this is SimLab. For those who haven't seen it before, it's really a user-friendly interface. We have some icons here representing all the tools that we can use. For each of the menus, the tools and the icons will change accordingly. And going from each of those, let me just comment a little bit about it. The Solutions tab is where we will see all the physics and applications that we can solve. Structural, thermal, flow, electromagnetics, I've talked about them, but we can also do some other applications such as drop test, fatigue, even DOE and optimization. In the sketch menu, we have how we can create our own geometry, starting from sketch, and extruding that or doing some revolution to get the solid body. Then we have our geometry menu, which includes creating primitive geometries and editing those. Also editing capabilities by importing your CAD, so we can do some editing with this menu right here. Then we have the mesh menu, where we can go from the 1D, 2D to the 3D mesh, adding some mesh controls to it in order to specify the mesh size on a specific region, or even the mesh flow from a region to another, the transition between these mesh sizes that may differ from each other. Then we have the analysis menu, is where we can add the loads and constraints, initial conditions, contacts, connectors, all that will be stored right here. Then we have the results. So once you have solved your problem, we have here some tools that we can use in order to post-process those results, such as creating XY plots, defining and finding hotspots, and also frequency response. All right, so let's start with importing our CAD. I'm getting my T-port example imported right now. And here on my left wing, I have my model browser. Right now I'm in the assembly tree, so all these tabs is within the model browser. The assembly tree is where all the bodies and components that you have will be stored, not only CAD, but also the mesh models as well. So once we mesh this component, you will be able to see that there will be stored both the CAD and the mesh bodies. All right. The first thing that I will do for meshing purposes is measuring this. I'm gonna get just the bounding box for me to have some reference in terms of mesh size that I should define. And then I will check on this length right here. Check the length. So this is 4.1. Okay. The unit I have it enabled, but I have imported this model as millimeter. So all you've seen, this value right here, will be in millimeter, but you could also enable the unit system to work with a visible one. All right, let's go into the meshing process then. We could do a really straightforward tetra mesh onto this, but I'm gonna do some mesh controls because I want to define more than one layer to my thickness right here. So the first thing that I will do is add in a body mesh control. This will ensure that my average element size within this component is predefined. In my case, I'm going to define 6 millimeters. And as you've seen, the length right here for this edge is 4.1. So if I add 6 millimeters, this will make that this thickness will only have one element. And for that reason, I'm going to specify a number of tetra elements layers that I want to have. Instead of one, I want to have 2 layers to define this thickness. The reason I'm doing that is because I want to increase the precision of my model, and the more refined the mesh it is, the more precise it can be. There are some exceptions whenever you're dealing with some errors that may happen, but in terms of rules, whenever you mesh it, you'll get a more precise results until you reach a certain convergence for them. All right, so I have defined both mesh controls, body and a volume layer, which ensures that I have 2 layers right here. Now I'm going to do a simple tetra mesh, just opening this panel, hitting OK. And now my software is creating the mesh in the background, so I can see here the progress bar. Let's wait a little bit, just a few seconds for it to finish. Then we can check the elements inside and exterior elements as well. Okay, so we have our initial mesh. This will be enough for us in terms of precision. There's a few things that I will recommend: increasing the number of elements within the fillets where you might have stress hotspots, also in this other end right here. So these are typical points where you will see stress hotspots. You will see a higher stress in this region due to stress concentration factors that you have in the geometry. In my case, I'm going to leave it as it is for the demonstration purpose. So now we have both models. We have our CAD and we have our finite element model. With that, we can proceed to the solution setup. In my case, I'm going to start with the linear static one. I will select the body that I want to use. And I can see here that my model browser has changed to the solution tab. This is where all the inputs such as loads and constraints, such as contacts, such as coordinate system. All this will be stored right here in the solution browser. So let's start with a simple basic problem, which is a hydrostatic pressure due to the tea that is inside this teapot. So let's add that fluid as a hydrostatic pressure. In my case here, I have my density of fluid in kilogram millimeter cube, and we have my gravity in millimeter second square per second square. The selected phases that is needed to as input is the phases that we call wet phases. So we have these phases right here, which is in contact with the fluid. And then I'm going to define the fluid level so that we have a specific height of fluid inside of it. In my case, I'm going to use the XZ plane as reference and give a certain distance to it. So now we can see this plane. Everything below that will be covered in fluid. So this is all that I need for my pressure input right now. Graphically, there's no representation of the fluid, at least using hydrostatic pressure, but I can see here the load that has been created representing that. All right, after that, I can add my constraints. I will simulate right here somebody holding this handle using these nodes as reference. So a person is grabbing this teapot in this section right here. I'm constraining the degrees of freedom that previously had this pod. So that's all basically that we need in terms of loads and constraints to simulate my teapot example right here. In case we have multiple bodies, we could deal with contact. So we could add contact between both pods, and we could add another types of loads that we could use, such as bearing pressure or temperature. But in my case right here, we're going to stick to a simple hydrostatic pressure being applied due to the fluid inside of the teapot, and my node constraint simulating somebody grabbing it by the handle. After that, we should define what is the material that is made this teapot of. In my case, it's porcelain, so I have it stored right here on a file, an exterior file. I can right click to verify what are the mechanical properties, so we can check here the density, Young's module, Poisson ratio, and we can also check our stress limits. So for tension it's 15 megapascal, for compression 240, and for shear stress we have 30 megapascal. I'm going to select my body to apply that material and hit OK. That's all I need. Since we're running a linear static problem, we just need the stiffness itself and the loads to calculate the displacement. So from our previous equation, force equals stiffness times displacement, we have the force represented as the pressure, and we also have the stiffness, which is taken into account based on the material that we have selected right here. With that said, we can simply run by clicking on Update, and the solver will start running in the background, and in a few seconds we will be able to see the results and evaluate them afterwards. Okay, so we've got our results. With our initial result, we can see that the maximum stresses are around are close to our constraints. So we can check here, show min max. We can see that the max stress is located at this node right here. Let me just show you the node. So at this node right here, the central node, it's where we can see our max stress value in this case. We could also evaluate the displacement and the energy error density. And the minimum is around the other end, so we have this minimum at this side right here. One thing that you should consider whenever you're evaluating the result is if this value here is relevant for you, and the location where the stress is at. In my case, since this is close to my constraint, is not really where I want to evaluate in terms of stress. What I want to evaluate right now is where my stress concentration factors is present. So verifying the results in this region, we can check that the maximum stress value is around 0.9 megapascal, and comparing to our limits that we have in our material, for the tension stress, we have 15 megapascal. So this maximum that we have calculated after the simulation is really low comparing to that, which will result in a high factor of safety, something that we might not even need for this design, this amount of factor of safety. So in order to decrease this factor of safety, let's say a factor of safety of 4, we should consider changing the thickness of this model or changing geometric. This is our first consideration. We just evaluated this as a linear static problem, but what if this is not the consideration that we should take? Is this the correct approach we should take in order to design this teapot? In many cases, this question is really hard to answer because it takes into account the analyst's experience. And in my case right here, I'm gonna just try a different approach. Instead of just using a linear static problem, I'm gonna add some heat to this teapot to evaluate what will be the results whenever I apply some temperature on the bottom side of this teapot, and see how the stresses behave whenever I do this heating procedure. Now what I want to do is go into the thermal pod and do a steady state heat transfer solution. I'm selecting once again my teapot. And now as you can see in my analysis ribbon, all the relevant icons has changed in accordance to my solution that I have specified. In my case, thermal, all relevant tools will be added to do a thermal analysis. As loads and boundary conditions for the thermal solution, what we're going to add is a fixed temperature of 300 degrees on the bottom side, simulating that we're heating with the cooktop, let's say. And we also will add the convection due to the air and also due to the fluid internally. So let's go into it. Let's add initially the temperature. Let's select our bottom phase, which is the phase that is being heated. A constant value of 300 degrees Celsius. And then we're going to add the convection from the air. So we have our temperature 20 degrees Celsius with the film coefficient 0.01. Let's select the outer faces right now. Apply. And now I'm going to add a 90 degrees Celsius convection. That is my body in contact with the fluid inside of it. So my tea heated at 90 degrees Celsius. So this is my tea temperature right now. So I'm adding also that convection due to that fluid. All right, that's all we need in terms of thermal steady state heat transfer. We have added the temperature as a constraint, let's say, a temperature constraint, and we have added the convection as my loading, let's say. Now we can add update, and we can calculate the temperature distribution throughout our entire body. All right, we've got here the results. As we can see at the bottom side, with the red color represents the high temperature and the blue color a lower temperature. At the bottom at 300 degrees, which was the predefined value for the temperature at the bottom pod. And then we have this temperature distribution due to the cooling process of the convection. So we have an air film covering the outer side and the fluid film covering the inner side. And this is pretty much what we get out of the steady state heat transfer in this case right here. We can then check, for example, the temperature at the handle. So we can check that the value right here is around 30 degrees, which is acceptable to someone to hold it. we've got our thermal distribution, but this doesn't show us anything about the stresses. It's just the temperature, degree temperature around my component. So the thing that I need to do right now is get back to my structural simulation. Let's set it as current. So I'm getting back to my structural simulation. And now what I'll be doing is include my temperature result and my loads and constraints right here. And to do that, I can simply include the temperature from that specific load case that I did. In my case, the solution thermal. Okay, now we can see this marker right here representing the temperature distribution. We can check also the contour of it. So it's equivalent to what we had in the thermal analysis. And now we can simply run it and verify what will be the stresses based on the hydrostatic pressure that we have applied and also the mapped temperature from our thermal case. All right, now we've seen some changes around the value, and what we can take out of that is that from 0.9 megapascal, by adding a different consideration to our problem, which was adding a heat source on the bottom side, we now see that the stresses are higher than our allowed stress from our material that we've seen. So 15 megapascal for the stress, the tension stress. We can see that this value is higher than it. So in that case, our body wouldn't, let's say, survive to that specific loading. This way, the porcelain will break apart and it won't resist to this heating source at 300 degrees Celsius. So all that was just to tell you that whenever you're trying to represent something from nature as a physical problem, be aware that many things can be taken into account in that problem definition, because a simple thing that I did, just adding a different application to this problem, which was heating up my teapot, made my problem go from a safety factor of more than 10 to something that wouldn't resist. We've talked about only these three blocks right here on the top part. But after our finite element solution, we need to verify the solution accuracy and results, interpret those results. In case we feel there are more things to be added in that solution, we need to refine our analysis. And two ways of doing that is improving the model, the mathematical model, or even modifying our physical problem itself. This is what we did in our case. We modified our physical problem, and therefore we received different results due to that. And this is something that you also need to take into account whenever you're doing this system idealization stuff. So that's it that I wanted to show you in this presentation, covering really the fundamental process about finite element method, how to define a problem, how to create the mathematical model out of it, and calculate using finite element method, and also showing that how it is the workflow inside SimLab, how can we do create the mesh, apply the material, define the solution, set up all that solution, adding loads and constraints, and verifying the result and interpreting that result. Thank you for your attention, and in case you have any questions, I'll be here to answer you as panelists. Thank you very much and have a good day.